So today, I would like to continue talking about compact Lie groups and their homotopical generalizations. So remember, the motivation for this problem came from giving a homotopical characterizations of compact Lie groups. Okay? So last time I gave you this theorem called the Maximal torus conjecture. Well, originally called the Maximal torus conjecture, that said that a space is homotopically equivalent to a compact Lie group if and only if it is a finite loop space with a maximal torus. And then I promised that I was going to explain what all the terms in this theorem meant. So that's what I'm going to continue to do today. So yesterday I said that, well, one initial step to see compact Lie groups from a homotopy point of view is to consider that the multiplication is a multiplication up to homotopy. Hence, we were looking at H spaces, right? And when we look at H spaces, we already saw that the rational cohomology had this nice expression that we wanted. It was a rational stereo algebra, and the number of generators, well, had a name that we called it the rank, even though in that case we may not have maximal tori. But like I said at the end, compact Lie groups not only are H spaces, they are also loop spaces. And how are they loop spaces? Well, this had to come eventually, classifying spaces. I mean, for finite groups, we've been talking about classifying spaces a lot. So it's natural that they will come up for compact Lie groups too. Now, for finite groups, we define classifying spaces as the realization of a certain category, right? Now, for compact Lie groups, you can also do that, but you will need to do what Roberta was explaining yesterday, to take a topological category, where the space of the objects are really a space, and the morphisms are also a space. But instead of that, I'm gonna do something that's a bit simpler, and that also Mark told us about it, the Milnor construction. So there is a way, if G is a compact Lie group, and in fact, this construction works for any topological group. Milnor defined a space called EG as the direct limit, or as the union, if you want, of spaces E and G. And these E and Gs were given by joins of the space G. So this will be n times. Yeah. Now, all these spaces have an action of G by multiplication on the left. I mean, we can think of these like as linear combinations, as convex linear combinations of elements of G. And therefore, this EG also has a free action. So EG has a free action of G. Also, the thing about these spaces E and G, or more concretely about this construction join, if you've ever seen it in a topology course, is that every time you do join, you increase the connectivity of the space. So these spaces E and G are increasingly connected as n is higher, up to the point where we get that EG is contractible. Okay. Well, in this case, the classifying space for my groups is going to be the orbit space under the action of G. Okay, so this is going to be my classifying space. And as it happens, if we look at this Well, because the action is free, this happens to be a principal bundle. Oops. Okay, but then we are again in the same situation as we were in the case of a finite group. Right? We have our group over here, we have a classifying space, and in the middle we have something that is contractible. So we can again do the same process that we did and show that loops of BG is homotopy equivalent to G. So we also have, therefore, G is homotopy equivalent to loops of BG. Okay? So we already did that one of the first days. Well, now this is good. I mean, not only is G an H space, is the loop space of something. Yeah? So then I want to consider this situation in a more abstract way. So what is a loop space? A loop space is a triple X, Bx, E, X to loops of Bx. So it's a triple of one is a space, well, two spaces, and a homotopy equivalence from one to the loops on the other, where Bx is a connected point space. Okay. I mean, many times we will say that X is a loop space, but we would like to keep track of at least X and Bx, because many of the constructions will be doing it directly from the classifying space. I mean, here we are not constructing Bx from X. We have an abstract space Bx, such that the loops on this space is X. But by analogy with this, we will call Bx the classifying space of X sometimes. Okay? What was I going to say? Oh, and here I mentioned the adjective finite. So what do I mean by finite here? So we say that the loop space is finite if X has the homotopy type of a CW complex, of a finite CW complex. All right, this should make sense, because if we think of G, G is a differentiable manifold, so it should be also, it should have the homotopy type of a finite CW complex. Okay, so let's write that. A compact D group is a finite loop space. So far so good. But now we have to think of what a maximal torus is. I mean, here we don't properly have a multiplication. I mean, we have a multiplication up to homotopy given by this equivalence. So what should be a maximal torus in this case? Well, maybe we should think first of what should be a subgroup of a loop space. Right? So let's think of what should be a subgroup. Now, for that, let's think of the case of compact Lie groups first. If we have a subgroup H of a compact Lie group G, well, we have a map induced on the classifying spaces. This construction satisfies all the properties that for finite groups. So we have a map from BG to BH, from BH to BG. And the homotopy fiber of this map is homotopy equivalent to G over H, okay? Well, the space of cosets. And this is again a finite dimensional differentiable manifold. Yeah. So our generalization for a subgroup of a loose space is going to be through the classifying spaces using this. So let me write that. This is a finite dimensional manifold. So now a subgroup of a loop space is going to be a map from By to Bx, such that when we look at the homotopy fiber, the homotopy fiber is finite in that sense. So it's homotopy equivalent to a finite CW complex. Okay? I mean, this is the idea of what we are going to do, is trying to rephrase everything in terms of classifying spaces. Does this make sense? It's a really quiet crowd. Okay. Now let's think about what a tori is, or what a torus is. Torus is a product of circles, but now we are going to look at that through their classifying spaces. So a maximal torus for a loose space, well, it's going to be a map from the classifying space of a product of circles, so the classifying space of a torus. We again want the same condition, that is a subgroup. So we again want this to be a finite CW complex up to homotopy. But also we want it to be maximal in a certain way. And the maximality can be expressed in the following way. If we count how many S1s are here, so let's say this is a torus of dimension n, we could think of that as the geometric rank of X. But we also have another notion of rank that comes from looking at its rational cohomology, right? So we want that n be equal to the rational rank of X. So we want the two notions of rank to coincide.
Is it possible to have?
Now, in general, we don't need to have a maximal torus for a finite loose space. If we did, then it will be, by the maximal torus conjecture, it will be a compact Lie group.
And can you have like n plus 1 copies of? Can you have?
Can I have more? No.
That are bigger than the ring?
No, no. I mean, you can also check that this is a maximality condition in the sense that if you have a map from B, T, n plus 1 into X, then the homotopy fiber cannot be a finite CW complex anymore. Yeah, that's a good question. And like I was saying, even though I was not answering the question, I was just answering my question, not every finite loop, even if we put the finite condition, not every finite loop space need to have a maximal torus. Yeah, a maximal torus is something that characterizes compact Lie groups. But let's go back in time before we even had this maximal torus conjecture. So say in the 40s, 50s, and 60s, there was a lot of studying done on finite loop spaces, and H spaces too. But at the time, there were not that many examples. I mean, we had compact Lie groups, and then we had the 7-sphere, at least in the simply connected case. So these were really all the examples that we had. And the 7-sphere is not even a loop space, it's just an H space. So at the time, there was a conjecture that this one is not true. So there was a conjecture from the 60s that said that every finite loop space will be a compact Lie group. Every finite loop space is a compact Lie group And also for H spaces, every finite H space is a product, well, is it's homotopy equivalent is the product of a compact Lie group and copies of, and a finite number of copies of the seventh sphere. Okay. Well, and this, I guess I should have said here at some point, simply connected. So if it's not simply connected, then we should also consider RP7. The projective space also has an H-space structure. Anyway, this is false. But this conjecture was still believed by some people at the beginning of the 60s, until the counterexamples came. And the counterexamples were not liked by people. I mean, the first counterexample was called the criminal. This is how little they liked it. So the first counterexample came in '69, and it was called the Hilton-Reuter criminal. So they really didn't like that that conjecture was taken down. But it was a good thing. I mean, it gave rise to a lot of new spaces and really interesting spaces and really new techniques like P-completion and all that stuff. So what did they prove, Hilton and Reuter? So they proved that there exists a finite loop space on Y. I'm going to omit the rest of the triple, which is not homotopy equivalent to a compact Lie group. And moreover, this space is not that complicated if we think of, I mean, there is no, I mean, but let me just say why it's not complicated. I mean, this space is the total space of a fibration, of a fiber bundle, S7 with fiber S3. And this Y, moreover, is a 10-dimensional differentiable manifold. I mean, it's even differentiable, so it doesn't look that complicated. But there it was. And it also satisfies some properties that people found disgusting in some way. A property that didn't satisfy is that it didn't satisfy homotopy cancellation. So they prove also in that same paper that SU2 product with SP2 is homotopy equivalent to SU2 cross Y. But because of that result, it's clear that we don't have, that these two spaces are not homotopy equivalent. So this is really interesting. And in fact, there was a lot of effort in this paper about homotopy cancellation, more than about finite loop spaces and compact Lie groups. Now, if one wanted to have some hope of classifying finite loop spaces, one was hoping for a result like compact Lie groups. Every compact Lie group is the product of simple groups. And this decomposition is unique up to permutation. But if we don't have homotopy cancellation, then that's not possible anymore. So a simple classification of finite loop spaces was already thrown out the boat. And that was bad in a way. But on the other hand, it was good, because now a new set of examples started coming. So another blow to the theory of loose spaces and edge spaces was given by a theorem by Rector. I don't remember the date of this, but it's around that time too. And this is really a surprising result. So Rector proved that there are uncountably many distinct, I have trouble finding the statement of this. Uncountably many homotopically distinct, yes, that's the right statement. Homotopically distinct spaces C such that loops on C is S3, the 3-sphere. Okay? So I mean, the 3-sphere, we can think of it as this, well, apart from the circle, as the simplest compact Lie group that there is, SU2. Right? But then here is Rector and says that SU2, if we look at it as a space, sorry, I just put here to homotopy. If we look at the 3-sphere, SU2, just as a space, it has many different multiplications, right? Many different loose space structures. And not only many, uncountably many, which is a lot, yes?
So is that equivalence like preserving a multiplicity?
No. No, but I mean, if you look at, so if you look at how different the multiplications are, there are not uncountably many multiplications.
So I can put that many multiplications on S3.
On S3, yeah.
And they're all distinct.
Yeah. But this, on the other hand, was also a clue of what's happening. And the clue here is that maybe one shouldn't look at the space itself, but one should look at C, and not try to classify the spaces, but classifying the C, that is the classifying spaces. So this was kind of a switch from approach, from looking at the space to looking at the classifying space. Also, all these spaces, this and that one, even though the construction was not done using, well, at least this one was not done using localization or completion or anything, they have in common that, in a way, they could be done using homotopy mixing, just like Zachary was telling us yesterday. So let me tell you a bit about that. So here we have the result. We have uncountably many homotopically distinct spaces. But what happens if instead of S3, we look at just a particular prime, and look at the 3-sphere completed at P, and ask the question, how many homotopically distinct spaces are there such that loops on that space is homotopically equivalent to that? We're asking for this now. And in this case, the answer is that there is only one. So it's unique up to homotopy. Okay. Of course, this was not known at the time. This is a result now from '86. Yeah. And also, although I haven't seen this proof anywhere, or maybe I don't know where the proof is, to be more honest. If we look at the rationalization, there is also a unique one, also a unique up to homotopy. Now, if we remember, I mean, Zachary was talking about localization yesterday, but also about P completion. These are the pieces of the space, and one is usually able to recover the space from all these pieces. So when one has, if you have a space, so you have a space X, and you look at all their completions, so you look at the completion xp1, xp2, xp3, etc. And then you look at the rationalization. There are maps coming this way. And one can recover X as the homotopy limit of this diagram. Yeah? I mean, up to homotopy. You can recover its homotopy type. So what these two examples have in common is that if you look at the pieces, well, they have to be the same pieces, because at the end you get the same space, S3. But the difference is how you glue the pieces. So here, if you have all the same pieces, what you do is before you do this map, you do an automorphism of this guy. And then this map is twisted. So when you glue them, you get a different space, but all the pieces are the same. And I mean, we have that many primes, so that's how Rector got the uncountably many pieces, by doing automorphisms on each of the spaces and then gluing like that, okay? So I mean, this paper by Rector is really interesting. I mean, it's mind-blowing in my point of view. So if you have a chance to take a look, I really recommend it. So anyway, we are at a bad point, I guess. But on the other hand, people started realizing that this was the only problem. So the point of view has to be switched now, not only to the classifying space, but also looking things one prime at a time. Okay, so now I want to talk about p-compact groups. All right. So first, I'm going to give you just an exercise for this afternoon is that if you look at an odd-dimensional sphere, right? Well, in general, an odd-dimensional sphere doesn't have a product. The only H spaces which are spheres are S1, S3, and S7, well, and S0 too. There are only 4 spheres that properly have a multiplication. But when you only pay attention to a prime, these happen to be H spaces. They are H spaces, well, when P is odd. Okay? So I'll give you more details about this construction in the afternoon, sort of break it into parts for an exercise. But I'm more interested in loose spaces. So a question is, well, how many of these are loose spaces? Maybe some of them are, maybe some of them are not. So this is actually an interesting computation, and it was done at the same time that Sullivan introduced the p-completion. Yeah? So when Sullivan introduced the p-completion, he did this interesting example. When he looked at the, well, let me give a name to this. I'm going to talk about the Sullivan spheres. And this was done in 70. Okay, so the construction goes as follows. Sullivan looks at the p-completion of the integers, okay, and considers the units. Now, what are the units of the p-adic integers? Well, they are the elements whose, well, remember that the p-adic integers can be written in this form. They are like infinite sums of things of that form. So the units are precisely the ones for which A0 is not 0. Right? And then A0 can go from 0 to p minus 1. turns out that this is isomorphic to Cp minus 1 times Cp hat. Okay? Okay, so now this is a finite group. Yeah, Cp minus 1. Well, this one is torsion-free. But this is the interesting part for what I'm going to do now. Now, there is a way to put a cyclic group in here, Cm. Well, we can put it inside if we know that m divides p minus 1. Yeah? And this is giving us an action of Cm on the p-adic integers. Yeah? Well, if we have an action there, we also have an action of Cm on KCp2. An action there is going to induce an action in here. And this space is also the p-completion of KC2, which is the classifying space of a circle. So this is BS1, p-completed. So let me tell you why I'm doing all these mysterious things. Okay? Let me erase this just to make room. We can think of this guy as GL1 of Cp. Yeah? So what we have here is a finite subgroup of a linear group for some ring. Right? Now you remember back yesterday we were talking about the general linear group for C. Now we change to Cp. And this is telling us that, well, this is giving us an action of Cm on a torus, kind of like the action of the Weyl group on a torus. Only here we have the action on the classifying space MP completed. But, I mean, there has to be some change. But you definitely see the analogy with compound Lie groups. Yeah? Is that processing? I mean, there is definitely an analogy. Now, the construction that we're doing now, that Sullivan did, is look at the Borel construction. So look at the Borel construction. This space. Now, this sits in a fibration over BCM with fiber BS1 be complete. Well, yesterday we were talking about fibrations that can be completed and fibrations that cannot be completed. Well, this is a fibration that can be completed. So we can complete this fibration. And this space is P good. So when you complete it, again, you get the same thing. BCM be completed. Wait, let me see this one. Sorry. All right, so this space in the middle is the interesting one for us. So Sullivan called this space Bx. Okay. And then, using the Z spectral sequence with coefficients in Fp, so using the Z spectral sequence, Bx is just notation. So this is, let me put Bx definition. So we still don't have an x. But this is going to be the start of a finite loop space. So then x is going to be loops on that. So using the Z spectral sequence, then he computed the cohomology of this. And this is also an exercise for this afternoon. It's not hard to do. So it turns out that the cohomology of this was isomorphic to a polynomial ring on a generator in degree 2m. Okay? I mean, you think about the set spectral sequence, you're going to have cohomology of this guy. It's going to be sort of like sorry. You're going to have the cohomology of this guy that is sort of like a well, the cohomology of BS1 is a polynomial algebra on a generator of degree 2. So what's going to happen is that this guy is going to act there as a multiplication by an mth root of unity. So the one that is going to get fixed is the mth power of that generator, and that's here. But anyway, the details I'll leave it for this afternoon. And if we now look at the path space vibration, then we can compute the cohomology of the loops on that guy. And this is something that probably many of you have done already, that if the cohomology of something is polynomial, then the cohomology of the loop space will be an exterior algebra on a generator of degree 2m minus 1. Okay. But you recognize this as the cohomology of the 2m minus 1 dimensional sphere. Yeah? Well, this actually is giving us, so therefore, loops on Bx is homotopically equivalent to S2m minus 1 P complete. Sorry? No problem with fundamental group because I probably should assume that. Thanks. Probably should say something here about M. Let's say that M is bigger than 1. Yeah. So that there is no problem with the fundamental group. So then these spaces will be simply connected, all of them. And we get this equivalence because remember, P completion, I mean, to have an equivalence in P completion was equivalent to having an isomorphism on FP cohomology, right? And this space is P complete, right? We have Bx is the P completion of something. So that's where this equivalence is coming from. Is this clear? Yeah. All right, but in particular, we proved something very interesting, is that even though not all dimensional spheres are loop spaces, these ones are. So we proved that S2m minus 1. Yes?
Where is the math S2m minus 1 into loops Bx?
Oh, well, you have a cohomology class in here. In dimension 2m minus 1. And that's giving you a map also from S2m minus 1 to loops on Bx. That's where the map is coming from. So, like I was saying, we proved that this is a loop space if, what was the condition? If M divides P minus 1. And one can also prove the converse, that these are the only spheres completed at P that are loop spaces. Okay, so this was an interesting example, and it was an example that was generalized not shortly after by Clark and Ewing. So now, we kind of mimic the beginning of the construction. But now we want to have not the units of CP, but we want to look at GLN of the periodic integers. And find finite subgroups of this. So we want to find finite subgroups And we also need a condition that P does not divide W. And well, this condition, now you may not see why, but if you look at the spectral sequence here, you will realize that the spectral sequence collapses really quick because of this condition. So anyway, because we have an inclusion here, we have an action called W on an n-dimensional torus. So now they define Bx to be the Borel construction on KCP2 to the n P completed. And remember that this is the same thing as B S1 cross S1 n times P completed. Oh, yes, P completed. So again, the same analogy. So what they prove again, using again the same argument, is that the cohomology is a polynomial algebra. It's a polynomial algebra on a finite number of generators. And then using a similar argument, if we take the loop space of that, well, we get that the cohomology is finally generated. I mean, maybe you get a bit more, but let me just say that you get finally generated. So you also get that the cohomology on the loop space P is finally generated. Or, well, let me just say, since this is a field, you can say that this is a finite dimensional. It's finite dimensional over FP. Now, you have to think that this is something not common. I mean, when you do loop space on a space, what you get is something usually bigger than the space. The cohomology, most of the time, is going to be something huge. So to have something like that, where the cohomology of this loop space is something finite, at least in this P local sense, is not something common, right? So now when people were thinking now, well, now we have to study classifying spaces, and we have to study them from the P local point of view. So, okay, that's fine. But if you want to have an analog of a finite loop space, you need a finiteness condition. And the finiteness condition is going to be precisely this one. So this is going to be the analog of a compact Lie group in our sense. So this led to, well, there were many more examples that I'm not going to mention, just a question of time. But there were many examples that eventually led to a definition by Dwyer and Wilkerson. And this is really a paper that everybody should read. If you haven't read it, put it on your bucket list, because this is a must read. It's a beautiful paper. So they define what a P-compact group is. So a P-compact group is a loop space. Remember X, Bx, E. But now we're going to change the finiteness conditions. And we're also going to put some conditions of Bx, some technical conditions, so that arguments like that will work. So we're going to say that Bx is a P-complete. So where Bx is P-complete, now remember from Zachary's talk, this means that Bx is homotopy equivalent to its P-completion. And the cohomology of X with coefficients in Fp is finite dimensional. Okay, makes sense? Okay. So now, what are examples of p-compact groups? Well, we already seen a couple. Sullivan spheres are p-compact groups. Clark-Ewing spaces are p-compact group. And maybe let me add here too that when they did this construction, they also classified all possible groups that appear here for each n. There are also some examples that, of course, should come up here is, well, a p-compact group is a generalization of a compactly group. They should fit in here too. Well, not quite, but almost. So another example of p-compact groups are compactly groups G such that the group of components is a finite p-group. I mean, if you're thinking about simply connected, there is no problem. I'm sorry, about connected compactly group, then that's fine. But of course, we would like the theory to encompass all compactly groups. The reason why not all of them are included in this definition is precisely because of this p-complete part. So when you p-complete, I mean, that's going to have an effect on the group of components, right? And we saw that p-completion behaved well with respect to p-groups, but in general, not with the others, right? So this is what the problem is coming. But anyway, this is not a big problem because one can always work with connected compactly groups. And I mean, that's general enough to be satisfied. Also, if I have time at the end, I will say that this p-compact group is still not the most general generalization. General generalization, that's a bad way to phrase it. There is a further generalization that kind of takes together compactly groups and finite groups, right? And we're going to be able to get rid of this condition. But let me not get ahead of myself and continue talking about p-compact groups. So the thing about p-compact groups is that they are surprisingly well behaved. They have maximal tori. So what is a maximal torus in this case? Well, it's a map from Bt to Bx, where now Bt is Bs1 cross S1 a number of times, say n times, P completed. It's just for notation. I don't want to carry the P completed here all the time, so I'm going to denote it like that. Again, we want the fiber to have a finiteness condition. Now, you remember for loose spaces, we wanted the fiber to be homotopy equivalent to a finite CW complex. Now, the finiteness condition is going to be P local. So we want the fiber to satisfy that the cohomology of F for Fp is finite dimensional. That's the finiteness condition now. And we also want this rank to coincide with kind of the rational rank of X. But now the rational rank is a bit harder to define because these objects are P-local spaces. So rational cohomology doesn't do justice to P-compact groups or to P-local spaces. We need to use P-local cohomology to recover all their features. So we have to look at the cohomology of Bx with coefficients in CP completed, tensor with Q. And now this turns out to be always, for P-compact groups, a polynomial algebra on a finite number of generators. Yes. Okay.
So like if you have space and you want to get P local information, why use FP there and for P-adic entry?
Okay. Well, in general, okay. So the answer, the question was why use FP sometimes and why use ZP other times? Just more or less. Well, the answer is we use FP in general most of the time because we want to relate cohomology isomorphisms with homotopy equivalences in P completion. Okay, that's why we use FP. Now, the reason why we need to use CP in here is that if you look at the cohomology of Bx with coefficients in FP, in general, it doesn't have to be polynomial. It will be a bit more complicated. You can get torsion. And the reason why you get a polynomial here is it actually comes from algebra, right? It comes from algebra in that I haven't talked about it yet, but there's going to be also Weyl groups. And Weyl groups are going to be finite subgroups of these guys, but without this restriction. And they are going to be generated by reflections. Now, our result in this theory is that if you have this guy, this is isomorphic to the cohomology of the maximal torus, which I haven't finished defining yet, but I will, with coefficients in CP, tensor Q, fixed points by the action of the Weyl group. Sort of like in the case of compactly groups, we have a similar thing with integers. Yeah. So our result in algebra, well, before I say about the result in algebra, this cohomology is a polynomial algebra. That everybody has to agree on that. When I tensor with Q, still a polynomial algebra over this ring. Yep. So there is a result that says if I have an action of a finite group on a polynomial ring, then the fixed points are polynomial again, if and only if that group is a reflection group. So it is a finite subgroup generated by reflections. Well, is it an if and only if? I think it's an if and only if. Definitely, if it's a reflection group, then this is a polynomial algebra. But we need to use these coefficients. We need to use the same coefficients that the group is a reflection over CP tensor with Q. Does that answer your question? Yeah. So, it's a question of having an easy thing to study, and a polynomial algebra is definitely something, like the easiest algebra that you can get. So anyway, to complete the explanation of what a maximal torus is, for this torus to be maximal, we ask that n is equal to this number of generators. Okay, which is kind of like before, right? Before we wanted this n to be equal to the rational rank, so analogous. Now let me also say that this condition can be expressed in different ways. So remember, in the case of compactly groups, we want our torus to be self-centralized. We want the centralizer of the torus to be T again. We can also talk here about centralizers. Our centralizer has to be defined in terms of classifying spaces. That can be done. You could define C BCXT to be maps from BT into BX. Well, and the component of, if I call this I, the component corresponding to I. This turns out to be the right definition. And as it happens, a torus is maximal if and only if it's self-centralized for connected P-compact groups. I'm not going to prove that, but just telling you that there are other definitions that are a bit more not so abstract as that one. So anyway, I talked about maximal torus. They also have a Weyl group. Now, how does the Weyl group work? So they also have a Weyl group. So what is the Weyl group in this case? The Weyl group, W of xt, is a set of components of the following thing. We want to look at homotopy equivalences from BT to BT over Bx that make this diagram commute up to homotopy. Only here there is a slight technical point that I'm not mentioning, is that we should replace this map first by a fibration. But up to that. Now this is a group, and it turns out to be a finite group. And we see that this group is acting on BT, right? It's acting on BT. And therefore, they are acting, it is acting on pi 2 of BT. And pi 2 of BT is n copies of that. So that's how we are getting the inclusion of this group as a reflection group. That's how we get the inclusion of WXT into GLN CP. Okay? And again, like in the case of company groups, if we tensor with Q, they turn out to be CP tensor with Q reflection groups. So they are CP tensor Q reflection groups. Okay? So we definitely have all the same elements that we have for company groups. And the classification of company groups was done completely through the reflection groups and the root data. Yeah? Well, the root data associated to these reflection groups. Now, in this case, one can also define root data over the p-adic integers. And one can also go through a classification. Because at that time, it wasn't necessary to do that because it was already done like 50 years ago. It was something that was already studied by Shepard and Todd, and then by Clark Ewing. So there was already an algebraic classification of all the CP reflection groups. And at the time, the P-compact groups were defined. Many of these, for many of these reflection groups, people had constructed P-compact groups which corresponded to these reflection groups, right? So at the time, the question was, well, can we construct one for each of them? And then, are these all that there are? And as it turned out, that was the right strategy, and people eventually constructed one for each. And the classification was that they corresponded to, well, not a one-to-one correspondence, because there are some root data that correspond to the same reflection group. But so let me give you the classification theorem. So classification is due to Andersen, Grodal, Moller, Viruel, and this is (2008) for the case of P odd, and then Andersen and Grodal finished the classification for P equals to 2 in 2009. And the answer is that every P compact group is a product of a finite number of irreducible P compact groups. By irreducible, I mean that they cannot be broken into a product. Okay? And moreover, this product is unique up to permutation of factors. So see how far we were when we were talking about finite loop spaces or having a classification like this. It was impossible. I mean, the results of our rector told us that we couldn't do that. Well, and also the fact that we that we didn't have homotopy cancellation. But in the P-local world, we do have homotopy cancellation. And that's part of a key. Yeah. Well, also I should tell you, probably wondering, what are the irreducible ones? Otherwise, so the irreducible ones first, we have an infinite family. We have an infinite family called XMSN, which are called generalized Grassmannians. Where M, S, and N are positive integers, and S divides N. I'm going to say something about the prime. Let me just finish the irreducible. And there are also a list of 34 exotic examples. Well, they call it exotic P compact groups. But I had to explain what this means, because this classification depends on a prime, right? And not all of them are going to show for all primes. Yeah? So each of them will show only for a list of primes. That's the thing. For example, XM11 corresponds to the Sullivan spheres. So these are 2m minus 1 p. But remember that this only makes sense when n divided p minus 1. Yeah? So this P compact group only appears for the primes that satisfies that. Does that make sense? So for some primes, there are more P compact groups than for others. And the compactly groups are precisely the ones that appear for all primes. Okay? So for example, SUN corresponds to X11N. That's that infinite family. Well, we should say, oh, sorry about that. we should say it like that. But SUN is defined for all primes. So that's how you recognize the compact Lie groups inside this list. Any questions? Is this more or less clear? Yeah. So I mean, this is this is very interesting for a start because we have all these new spaces, right, which are very interesting to study. There are analogous to compact Lie groups in a way, and that also helps us understand maybe a bit better the classification of compact Lie groups. I mean, in some sense. All right, now let me give you some consequences of this classification.
So the cosmology of all these theories about the compact groups is also exterior?
Well, when you look at with coefficients in CP, tensor with Q, but not in general.
Even in the exotic case?
Even, well, it's kind of a coincidence, but for the exotic cases, yes, they are always, the cohomology are always exterior. Yeah. But as you know, even in the case of compact Lie groups, the cohomology is not always exterior, right? You have some torsion too. But the case of exotic turns out to not have torsion, these exotic ones. There is some torsion in some of these too. Yeah. All right, so some consequences of this classification. One, well, the maximal torus conjecture. Right? Maximal torus conjecture said that we needed to have a maximal torus in order to be a compact Lie group. And, well, yeah, because compact Lie groups are the only ones that have a torus in every prime. I mean, all the spaces have a torus at each prime, but only compact Lie groups will have it at that prime. Another consequence, we now understand better finite loop spaces. Even though they are hard, we know that finite loop spaces are built out of these pieces. So they are built out of P compact groups. Right? As before, if you want to understand a space, you break it into this P local piece and the rationalization, and then you can recover the homotopy type from that diagram. So the thing here, we know what the pieces are. We only need to know how we can move these pieces, the automorphisms of each of the pieces. And each finite loop space has to come from choosing one for each prime, the rationalization, which is kind of given, and some combinatorial information, which is the automorphisms of each group, how we are gluing them together. It's still not an easy answer, because I mean, there are many components there, and the combinatorial information is not simple, but it's better than nothing. What else? Using techniques from here, not properly the classification, one can also prove that finite loop spaces are homotopy equivalent to closed smooth manifolds. And this is not obvious. I mean, a long time ago, people realized that finite edge spaces satisfy Poincare duality. And of course, the question came to mind, well, they satisfy Poincare duality. Is it possible that they are all homotopy equivalent to smooth manifolds? And that's still a conjecture. So it's still a conjecture, still open. Every finite edge space is homotopy equivalent to a closed smooth manifold. Well, I haven't said what closed is. Closed means compact and without boundary. So this is a conjecture that, as far as I know, is considered to be hard conjecture. And I don't think that much progress has been done lately on this, apart from that. So all these techniques help to prove that, which is an amazing result. And one question also that was proved using this technology is the steam rod problem of realizing polynomial cohomology. So maybe some of you have heard about this problem. It's an old problem that asks, given a graded polynomial cohomology, given a graded polynomial ring, graded commutative, is there any space whose cohomology is that? Right? And if you look at, for example, in Hatcher, they dedicate some time to this question, but it was open for a long time. But now, it was solved using this technology too. Turns out that the spaces whose cohomology are polynomial are pretty much products of P-compact groups, of classifying space of P-compact groups. And that way you can also check which, you have a list, so you can check which ones are going to show up and which ones don't. I'm not going to write the whole statement because it's a bit long to write, but I can show you if you like. Now, with this, I'm going to finish talking about P-compact groups. But I would like to talk just in the few minutes that I have about the common generalization of P-compact groups and P-local finite groups. Okay? So I would like to talk now, briefly, about P-local compact groups. I know that some people don't like these names. They find them confusing. P-compact, P-local compact. They're the same thing, are they different? Well, this is a different thing. Okay, so here the idea is to try to generalize what we did with finite groups. Now, for finite groups, the interesting part, the interesting P part, came from the Zillow. Yeah? Now we want to see the interesting P part of a compact Lie group. Now, the interesting homotopic part of a compact Lie group, at least for the classification that we've been seeing, what is it? Well, it's the Weyl group. Yeah? And the Weyl group is a finite group. Well, if the compact Lie group is not connected, it's also important to see how many connected components it has. But that's also a finite group. And on the other hand, we also have the maximal torus. And the maximal torus, we can also think of all the P torsion in the torus. Okay? So that's also P information in the group. So to generalize, we need to find a generalization of a finite P group. So definition, a discrete P total group is an extension of the following form. We have a C P infinity. This guy already came up. And a finite P group. So it is an extension of the P torsion of a torus by the P part of the Weyl group and the group of connected components. So all the interesting information about a compact Lie group should also be here. That was the idea. And that idea is true. So So definition, a p-local compact group is a triple SFL, just like a p-local finite group. But now S is a discrete p-total group, where S is a discrete p-total group. Okay, but the definitions of fusion system, central linking system are exactly the same. Yeah, formally the same thing. Well, at some point you have to put something to account for when you have sequences of infinite subgroups, but almost the same. Let me just say. I mean, you have the same axioms, and you need to add just a little extra condition. And this, well, and again, the classifying space will be this guy. But the class of p-local compact groups, I mean, in the sense that the class of these guys now includes many of the things that we see. I mean, they include p-local finite groups, because a finite is in particular discrete p-total, but they also include all compact Lie groups. They also include p-compact groups. They also include torsion subgroups of G, L, and K, where K is a field whose characteristic is different from P. And they also include some exotic examples. And exotic here meaning that they don't fall in any of these three categories now. But there are not many, there are only two, but there are two examples. I mean, it's still not clear how to build examples. And well, I'm out of time, so let me just say a bit about what I said last time. The relationship between p-compact groups and p-local finite groups was discovered later. I mean, at some point, I mentioned something about the Solomon group. So there was a construction of certain p-local finite groups which were exotic, and they came in a family. So L, Sol, N. So there was a family of p-local finite groups at the prime 2 that were inspired by the case of the Solomon group. And when you look at the classifying space, they all fit in a sequence. And if you look at the homotopical limit of this sequence, well, maybe I should put 2 since at the prime 2, and the homotopical limit over N, and completed at 2 again. This happens to be homotopy equivalent to the classifying space of DI4, which is the only exotic 2 compact group, right? So this gives you the relationship between these and those. Also, there are some operations called Adams operations on this classifying space, and when you take the homotopy fixed points, you recover these guys. So you can go back and forth. You can build them out of this, and you can also recover them out of that. So what Brotto and Moller did is once we have the classification of p-compact groups, they applied their homotopy fixed points under these Adams operations to all of these families of p-compact groups and to the exotic ones. And they found new exotic p-local finite groups, which is very, well, not for all of them, but some of them. It's really interesting. On the other hand, you remember I also talked about some families that Diaz, Ruiz, and Viruel found the classification of p-local finite groups over p groups of rank 2. And these ones didn't come from those. So here's the interesting thing. Then there was a PhD student there in Barcelona who took these families and realized that they could be put in a homotopical limit. And when you do that, you don't get a p-compact group, but you get a p-local compact group. And those are the only two exotic examples that we have, are the ones constructed from Alex Gonzalez. So anyway, of course, we still have much to understand about p-local compact groups. We don't have enough examples. So this is an area that's interesting to go into. And there's also some things that I haven't had time to talk about, which is p-local properties. But if you are interested, I can talk to you about it. Okay, I'll stop now. Sorry about the going over.